Hi everyone, my name is Germán Ruiz-Marcos and today I'm presenting a research project I have been working on together with Alistair, Willis and Laney at the Open University. As you can see, this project concerns the automatic calculation of tonal tension. In the literature, many authors have identified the concept of musical tension as essential to the listening experience. As a consequence, many scholars have attempted to model musical tension. These models normally study the relationship or correlation between different features and musical tension. These features can be either psychoacoustic, such as loudness, tempo changes, or onset frequency, among others, or can be cognitive features, which mainly concern melodic and harmonic motion. Models based on psychoacoustic features are, in general, easy to automate. You can probably think of different existing tools which automatically calculate loudness levels or the onset frequency of a given audio signal. On the contrary, models based on cognitive features are most of the time theoretical. We believe this lack of automated cognitive models of tension is a gap that needs to be filled, and so we have been working on this project. Taking into account we are focusing on cognitive models of tension, let me borrow Lerdahl's and Krumholtz's definition of tonal tension, which they describe as the sense of tension created by melodic and harmonic motion. From the existing models of tonal tension, we believe Lerdahl's is the most complete. And that is because of 5 reasons. First, it considers rhythmic, melodic, and harmonic components as opposed to other existing models which just focus on one or two of these components at a time. Second, it takes into account a piece's hierarchical structure as opposed to other existing models which only calculate tension following the chords in a piece of music in a sequential way. Third, it produces quantitative values of tension which are valuable for researchers in music computing like us, as we can use these values to implement new computational tools. Fourth, its components connect with all the cognitive theories, such as those of Leonard Meyer, Norm Moore, Steve Larson's, Baruch, or Krumholtz, among others. And fifth, it has shown strong correlations against human judgments of tension. Let me briefly introduce how Lerdahl's model of tonal tension, or MTT, works. First, we need to select a piece of music. Then, we need to calculate its key and chord labels. Next, we need to calculate the piece's hierarchical structure. To do so, we need to use Lerdahl and Jackendorf's generative theory of tonal music, or GTTM. This theory consists of a collection of rules to extract the metrical components of a piece of music, its inner groups and patterns, and its hierarchical relations. Finally, we need to apply the rules in Lerdahl's MTT. MTT incorporates 2 different components to tonal tension. The first, harmonic tension, which in the literature is referred to as T-glob, concerns the vertical arrangement of chords and the cognitive distances between them. The second, attraction, which in the literature is referred to as alpha, concerns the horizontal arrangement of chords and the voice leading paths between chords. To calculate the values of harmonic tension of a given piece of music, we need to calculate the cognitive distances between the chords connected by the piece's hierarchical structure. To do so, MTT relies on Lerdahl's tonal pitch space, or TPS, which includes a quantitative method to calculate the distance between chords, in a given key, that might be perceived by Western listeners. Likewise, we need to calculate a collection of surface parameters, which concern 3 features: the chord's inversions, the chord's highest notes, and the role the notes in each chord play in the context of the piece's key. To calculate the values of attraction, we need to parse each of the inner melodies included in every chord transition, as well as account for the intervals within these melodies. And we need to use TPS's distance calculation again. Let me show you an example of the application of Lerdahl's model of tonal tension. So, MTT's first step is to pick a piece of music. Here we have the Grail theme from Wagner's Parsifal. I have chosen this piece because you can find a detailed explanation of what I'm about to say in the literature. The second step concerns the piece's harmonic analysis. As you can see at the bottom line, The theme is in the key of E flat major, and its chord labels consist of a very common diatonic harmonic progression. Next, we move into the piece's hierarchical structure. By applying GTTM's rules on the Grail theme, one will get the tree shown on top of the picture. This tree illustrates the importance of each note with regards to the whole theme. Finally, by applying MTT's rules, one can calculate the quantitative values of harmonic tension and attraction, which are shown in the middle space. The question now is, well, is there a way of calculating these values automatically? To answer the question, let me introduce Auto10 as in automatic tonal tension, which is, in fact, the core of my talk. Auto10 is the system we have developed to automatically calculate the contributions to tonal tension of a piece of music according to Lerdahl's model of tonal tension. As input, Auto10 needs to be fed with a piece of music, as well as with the outputs of its GTTM analysis, all these files in music XML format. In our project, all GTTM analysis files were calculated using the interactive GTTM analyzer developed by Hamanaka and colleagues, and which is publicly available. See the reference in the footnote for more detail. As output, Auto10 will produce the quantitative values of harmonic tension and attraction according to Lerdahl's model of tonal tension, like those we just saw in the previous slide. So how does Auto10 work? For the sake of simplicity, I am going to indicate how the steps one needs to take to apply Lerdahl's model of tonal tension, those which I have already described, are implemented in Auto10. First, the piece of music to be analyzed needs to be input by the user. Second, to calculate the piece's key and chord labels, Auto10 uses the toolkit Music 21 developed by the MIT. More specifically, it uses the modules Analyze and Chordify. The hierarchical structure is another input file. However, Auto10 transforms the input GTTM tree into a matrix to ease the upcoming calculations. Recall that these GTTM-related files can be calculated by the user using the interactive GTTM analyzer. To calculate the piece's harmonic tension, we have transformed Lerdahl's tonal pitch space components into different objects and its rules into functions which combine different classes. In this way, Auto10 is capable of calculating the cognitive distance between chords. Likewise, the surface parameters, those concerning the chords inversions and their melodic notes, are calculated by extracting data on the pitches using Music 21 and mapping these data with the weightings defined in Lerdahl's MTT. Finally, to calculate the piece's values of attraction, we have represented the chords in their melodies numerically to account for every transition and their respective intervals. To evaluate Auto10, we asked ourselves the following questions. Has Lerdahl's MTT been correctly implemented? And how accurate are the calculations of tension provided by Auto10? Although these questions may seem pretty similar, they are looking at very different things. With the first question, we wanted to check whether we had made any mistakes when implementing Lerdahl's model of tonal tension computationally. We carried out 100 test cases to give an affirmative answer to the first question. However, as I do not have much time, I am not presenting these test cases in today's talk, so please refer to the paper and to Auto10's repository. With the second question, we wanted to check how accurate were Auto10's quantitative outputs compared to those calculated when manually using MTT. You may be wondering why Auto10 might not be 100% accurate, now that we have seen, after answering the first question, that it has been correctly implemented. However, it should be noted that Auto10 relies on the accuracy of the GTTM trees provided as input. Recall that we took these from the interactive GTTM analyzer, as well as on the accuracy of the chord labels, which were calculated using Music 21. As you can imagine, neither present an accuracy of 100%, and so we ask ourselves the second question. To answer this question, we have carried out 3 tests using 4 pieces of music. But why just 4 pieces of music, and why these 4? As it has already been stressed in the literature, there exists a lack of tension-related databases. In the case of Lerdahl's model of tonal tension, these 4 pieces are the ones that have been analyzed and studied by Lerdahl and Krumholz in the past. Thereby, these are the most reliable and accessible data one could find when working on Lerdahl's model of tonal tension. Using this data, we have carried out 3 accuracy tests. A first test to study the accuracy of the chord labels found by Auto 10 compared to those in the ground truth. A second test to study the accuracy of the TTTM trees used as input in Auto 10 compared to those in the ground truth. And a third test to study the correlation between Auto 10's outputs and those given by the ground truth. Again, because I have not much time, I will be only focusing on the third test. You can find more detail about the other 2 tests, their statistics, and more data on the paper and in Auto 10's repository. Before we get into Auto 10's evaluation, we need to discuss how Lerdahl's MTT was evaluated. Lerdahl and Krumholz recruited a group of participants and asked them to judge the degree of tension they perceive when listening to the pieces of music shown in the previous slide. As an example, this figure includes a dotted line with the average values of tension perceived by the participants when listening to the Grail theme from Wagner's Parsifal, which recall has already been introduced in this presentation. Using this data as ground truth, Lerdahl and Krumholz calculated a multiple regression to find the most accurate prediction of tonal tension that MTT could give. See how the predicted values of tonal tension were seen as the dependent variable, and MTT's harmonic tension and attraction as the independent variables. The results include an R-squared value as a goodness of fit measure. Between parentheses, you can find the degrees of freedom, first the number of independent variables in the regression, and second the number of events in the piece of music -2. They also calculated an adjusted value of R squared to make it more comparable with other models for the same data that have different numbers of degrees of freedom. Likewise, they calculated the regression's coefficients, the betas, and the statistical significance given by the p-values. In this example concerning the Grail theme, we can see MTT's predictions of tonal tension, the blue line in the figure, strongly correlate with the degrees of tension perceived by human listeners and are all statistically significant. To test the accuracy of Auto 10's outputs, we have followed a similar methodology. However, in this case, the ground truth data are the predictions calculated by MTT in the previous slide, which are shown again with the blue line in this new figure. The independent variables correspond to the values of harmonic tension and attraction calculated by Auto 10. In this way, the predictions of Auto 10 that best fit MTT's ground truth are those shown by a dotted line in the figure. I will be showing the data corresponding to this multiple regression in the next slide. This slide shows the results of the previous multiple regression, the one concerning Wagner's theme, as well as the results of the rest of the pieces for similar calculations. For each piece of music, there is a value of R squared and the degrees of freedom N and M, an adjusted value of R squared, and the p-values corresponding to harmonic tension and attraction calculated by Auto 10. By looking at the R squared values, that is the first column, it could be seen all regression shows strong correlation with that of Chopin, whose correlation is healthy, and are all statistically significant, as indicated by all p-values included in the last 2 columns. Unlike the rest of the pieces, Chopin's is constantly modulating through different keys. In fact, the prelude's last 2 phrases transition across 7 keys. We believe these heavy modulation processes hinder the automatic calculation of chord labels performed by Music 21, which, in turn, affect the final values of tension and could explain the lower accuracy in the case of Chopin's piece. Likewise, notice how, as the number of events increases, see Bach's and Chopin's rows, the correlation tends to decrease because there are more plausible points of deviation, as indicated by M, the second degree of freedom. In addition to the regressions shown in this slide, we also calculated other regressions to study the correlation of harmonic tension and attraction independently. Please check the paper if you are interested in these data and the respective discussions. To sum up, what is the message you should be taking home from this talk? Well, simple and easy. Auto 10 has been launched. It incorporates an automation of Lerdahl's theories, it is publicly available, and it has shown strong correlations against ground truth data. In future, we intend to produce a more detailed report of Auto 10's implementation. We believe the community will benefit from a thorough discussion about the computational challenges we encountered when automating Lerdahl's theories. Likewise, we have already started building a dataset of tonal tension based on Auto-10, which we believe can have a great impact in the community. Finally, we aim to explore the automatic generation of music with regards to tension using the doors opened by Auto-10, such as accounting for a piece's hierarchical structure. And that's it. Many thanks.